In quantum mechanics, there is a concept called as Heisenberg's uncertainty principle. Heisenberg was the scientist who gave this concept. Uncertainty principle, it tells us quantum mechanics does not simultaneously permit the determination of position and momentum of a particle accurately. If any effort is made to make the measurement of position of a particle accurately, then it results in a large uncertainty in the measurements of momentum, and vice versa. It means if any effort is made to measure momentum of a particle accurately, it results large uncertainty in the measurements of position of the particle. We can also say that in simultaneous determination of energy and time in a physical process, the product of their corresponding uncertainties inherently present in the measurement is equal to or greater than h upon 4 pi, which is equal to h upon h cross by 2. So from here, certain figures have been drawn. So as a waveform diagram, so first waveform diagram, it tells us that momentum precisely can be determined using this. So if the momentum can be determined accurately, there will be large uncertainty in the x. X is the uncertainty in the position. X, we say it is a position. So position is unknown if the momentum is precisely known. This is the equation given by de Broglie, who gave the idea the dual nature. So this is the de Broglie equations of the matter waves. So lambda is equal to h upon p. So here p is equal to h upon lambda. So lambda is the wavelength of the wave and p is the momentum of the particle. Wavelength, if it is there, that is lambda, it describes the wave nature of the particle, and momentum is there, it describes the particle nature. Okay. So here this is the sine waveform. It indicates that the particle is in motion. A wave is associated with that. A sine wave of wavelength. So wavelength means if you take this is the crest and this is the trough, one cycle. So complete the distance between consecutive crest or trough called as wavelength implies that momentum is precisely known. What the wavelength, wave function, and the probability of finding the particle psi star psi, which is known as the probability of finding the particle, is spread over all of the space. So here we can see that there are different wavelengths are there of different waves. So uncertainty goes on increases in the position. So if we take average of all the wavelengths, okay, so here the wavelength is very small and slightly more than that first one, and here more than the second one, and here more than the third one, and this is more than the fourth one also. So if we say wavelength are increasing, if we take average of the wavelength, so it is the momentum is accurately can be determined. If the wavelengths are more, momentum will be less. So different wavelengths together will produce an interference pattern if we take, okay, which may be constructive or destructive. Constructive amplitude goes on decreases, and constructive uh, amplitude increases, will produce interference pattern which begins to localize the wave-like kind of structure. So here we can say the wavelength, average wavelength is this much. So if the wavelength is less, momentum is large, uncertainty. So so we can say that, but the process spreads the momentum values and makes it more uncertain. So this is inherent and inescapable increase in the uncertainty. Delta P means uncertainty in the momentum. When delta X, uncertainty in the position is decreased. So here this is the waveform. It indicates that uncertainty in the position is increased if the delta P uncertainty is okay. So greater or equal to h cross upon 2 pi upon 2, which is equal to h upon. Now how mathematically it can be explained, uncertainty principle. So mathematically we can say that delta x into delta px greater or equal to h cross by 2. H cross can be written as h upon 4 pi. So we can also write in some of the books you will find that delta x and delta px they're greater or equal to h cross, it can be also, which is also correct. H cross can be written as h upon 2 pi. What is delta x? Uncertainty in the measured values of the position, and delta px, uncertainty in the measured values of momentum. So this was the equation given by Heisenberg, and greater or equal to sign is there here also as well as here. That's why it is called as the values are uncertain. So that's why the name is given as uncertainty. And why Heisenberg he selected only H cross. H cross is equal to H upon 2 pi as we know, and H is the Planck's constant, and Planck's constant is the smallest you can say constant in the physics. So whose values is 6.63 into 10 raised to minus 34 joule second. So if uncertainty values should be as minimum as possible, for that purpose he used the Planck's constant as the uncertainty greater or equal to be equal to of the order of uncertainty should be of the order of Planck's constant h. So that's why he selected as a h. Some important characteristics of the Heisenberg uncertainty principle we can see here means why uncertainty. So first is that it can be due to it can be as a direct consequence of the wave nature of the particle. It means whenever particle is in motion, a wave is associated with that. So because of the wave is associated with the particle, so it describes the wave nature. So due to that, uncertainty is increased. If only it is a particle, uncertainty is not there. But if is associated, so uncertainty is increased. The second reason can be the measurement is independent of the procedure or sophistication of the instrument. So it means that you perform the experiment related to uncertainty, position and momentum, either in the daytime or in the night time, or at different, you change the place also. You do the experiment here in India, and then you go to the Japan and some other places. So just and do the experiment at different temperature. In this way, we say that the measurements is independent of the measuring procedure and sophistication of the instrument, high quality of the instrument used. Then also uncertainty was going to come. So that's what all these studies have been done, and then it was concluded these type of points. One of the reason also, so why it was explained, it may be due to uncertainty, may be due to fundamental property of the nature. Means nature doesn't allow us to measure the correct values simultaneously, the position as well as momentum. So here it can be also applicable to the conjugate variables like energy and time, angle and angular momentum. Energy and time, it can be written as uncertainty in the energy, and uncertainty in the time should also be greater or equal to h cross by 2. And angle and angular momentum, angular momentum is L. So uncertainty in the angular momentum, uncertainty in the angle should be greater or equal to h cross by 2. Okay. Then we can also understand here some physical significance of Heisenberg uncertainty principle. So physical significance of uncertainty principle, it tells us one should not think the exact position or an accurate value of momentum of a particle. Instead, we should think of the probability of finding the particle at certain position, or of the most probably value for the momentum of the particle, but not exact value. And such probabilities can be calculated with the help of mathematical function known as probability density function. Okay. Now we'll move one applications of the uncertainty principle is this. How we can say that electron does not exist inside the nucleus. Actually, electron exists outside the nucleus. It revolves in particular orbit. So how we can say it? So quantum mechanics have this type of, you can say, answer. Yes, we can say by using Heisenberg uncertainty principle, we can say that electron does not exist inside the nucleus, it exists outside the nucleus. As we know, size, or you can say radius of the nucleus is of the order of 10 raised to 5 into 10 raised to minus 15 meter. And here we consider that electron exists inside the nucleus. So if the electron is to present inside the nucleus, let us say, so then we take electron may be present along its diameter. This is the radius. So diameter can be from here to this point. So electron can be here, or can be here, or can be here. On this line it can be. So maximum we are taking the uncertainty about its diameter as a position. So delta x is taken as in the form of 2 times radius, and so it becomes 2 into 5 into 10 raised to minus 15 meter, which will come out 10 raised to minus 14 meter as delta x, uncertainty in the position of the electron inside the nucleus. So within this nucleus, let us say this is the nucleus, and within this nucleus the electron can exist along its the diameter. Can be here, or can be on this side of the diameter, or can be on this side of the diameter. Okay, so if the electron is revolving, a wave is associated. So this is one wavelength is taken, lambda is associated, crest to another, okay, consecutive crest or trough distance called as wavelength. So here we apply uncertainty principle here, delta x into delta p greater or equal to h upon 2 pi. So if we calculate delta p, uncertainty in the momentum, because delta x we know, so which will come out 1 into 10 raised to minus 20 kg meter per second, because it is a momentum. So momentum mass into velocity, so unit will be this. And we can calculate therefore kinetic energy. It is of the order of momentum into speed of light, which can be of, once we substitute it, it will be 3 into 10 raised to minus 12 joules, which can be converted into electron volt, and then it is mega electron volt or million electron volt. 19 MeV energy is required, kinetic energy, if the electron is to remain inside the nucleus. But practically it is impossible for the electron to have such energy. Okay, so we say that electron does not exist inside the nucleus, but electron exists outside the nucleus, which can be seen in this diagram. Okay, so here we can say that all these are the here proton, neutron, nucleus, and outside there is an electron. Thank you.